Australia, big, empty, a long way from anywhere. It's the perfect place to automate. There are so many applications in Australia where you can apply robotics in mining, in materials handling, in agriculture, in marine environments, for defence, for bushfire fighting, you name it. If you wanted to do automation, Australia is the place that you'd come and do it. And in fact, in the last 15 years, Australia has gone from not too much to probably being one of the leading developers and users of robotics. And I think that often comes as a surprise to people. And some of that really is the reason that there are just so many good applications for this kind of technology in this sort of environment. So I'm going to tell you a story about how we got to this point. And I'm going to go back 20 years and show you, starting out, one of my very first robotics projects. And this was a pretty important project because it was one of the very first robots that went around with sensors, mapping the environment, trying to use that map to do navigation. It integrated planning, it integrated control. It did the sorts of things that you would like a mobile robot to do. And it was an important developer in a number of different ways. And we'll see this particular project impacting so many of the things that I've done, in fact, in the last 15 years as we go along. And it was interesting also, because we'll close the loop at the end, that actually one of the very early applications of this sort of technology was indeed in assisted care environments. So this was one of the challenges that we posed for ourselves at that time. So some of the technology from this went in fact, originally into developing AGVs for factory automation. So we worked at that point with Caterpillar, based in Rugby, to develop laser guidance systems for free-ranging AGVs that move components around a factory. And there are a lot of interesting lessons in there in terms of how you go about commercializing these sorts of things, the core technologies, navigation, control, guidance, systems engineering, and so on. But as I was doing this, I met an ex-army colonel in the UK, and he'd been actually commissioned to design a new container terminal. In fact, this is it when it's fully populated. And interestingly, he'd been asked to basically design the terminal so that it could be automated. No one had actually developed the automation for this sort of thing yet, but nevertheless, he was given the task of thinking about what you would do. And you'll see here, for example, there are rail-mounted gantries and things that basically attempt to make it easy to do this thing. And surprisingly, he and I actually got on extremely well. And we looked at this problem, and I basically said, well, how hard can it be? I mean, it's the simplest possible robotics application in some sense, because all you've really got to do is to pick up boxes and move them around, right? There is an issue, of course, of scale. So you're not moving around little boxes, they're big boxes. Speed, integrity, there's how you actually integrate it as part of an overall container terminal, things like that basically go on. But nevertheless, we got together, he got the money, and I got the technology. So I sat at my kitchen table, figured out, well, how do you build a very large AGV that can go at high speed? Problems to do with sensing outdoors. How do you see through rain and things like that? So development of things like millimetric band radar sensors. How you actually worry about safety. So you can never have one of these things running over someone. These are big vehicles. And at the commercial side, also, how do you actually go about developing some of these? These are capital-intensive things. You've really got to involve not just the terminal operator, but people who actually develop equipment, how you go about investing and so on. So, to cut a long story short, over a period of about 2 or 3 years, we developed this vehicle here, probably at the time one of the largest, fastest AGVs there were. It involved a huge amount of innovative research, and in fact I would be fair to say that if I'd done this as a research project, this would have been absolutely wow. It is only in a commercial sense that you get really forced to think about these things. So as I said, development of things like millimeter wave radar, interesting things here about how you actually model and control platforms like this, because as a load comes down, as you'll see in a minute, the entire platform deflects. So it's not a simple thing like you have an AGV in a factory. You've got to worry about things like tire radius changes, uneven ground, all these types of things. Real-time systems. Remember, this is 20 years ago. So getting computers to do all this processing and control at that time was a non-trivial thing. And how you actually go about integrating it, not just as a standalone AGV, but into the rest of the thing. There are a lot of commercial hurdles, and for me this was also an extremely valuable lesson about how you get the user to accept technology like this when they've never seen a robot before. How do you actually make a commercial case out of something like this? Is it cheaper just to have a driver or something like that? And also about issues of how you invest in these things. I think even more important about this project was all the failures that we made as we went along, because I think you learn a lot more from failing with something than you ever do by having a success. So some of you may know, I don't actually drive. I've never had a driving license. And you'll notice this vehicle is actually going in reverse at this point. And I had this algorithmic idea that, well, if you were going backwards in a car, surely if you want to turn left, you'd turn the steering wheel right. Okay? And I wrote the code to basically do that. And at this point, my colleague, who was also working on the project, realizes that actually I don't know how to drive. And there is a ripcord on the side here. And he's just about figured out at this point that the vehicle is not going to do what it said. So you learn from that process. And we did learn. We learned a lot about, for example, designing systems so that they actually work first time, every time. I also learned a great deal about commercial element of this end-user support, the need for support, and the fact that basically people are not going to invest in a startup company that's run by a bunch of academics, at least not at this scale. Okay? And it was a very valuable process in doing this. So by this point, I was no way I was going to work on indoor robotics anymore. It was much too much fun working on these large things. And again, if you live in Melbourne or you live in the UK, you don't want to work outdoors. So I decided to move to Sydney to continue this. So the field robotics bug was really big now. I thought big vehicles, big applications, if you like, the IBM 370 of the robotics world. We really were able to push the case in these areas. So I looked at what was out here, mining, agriculture, marine environments, and I thought this was the place to be. And there were nice pictures of beaches and things like that, and nice pictures of mines, which I thought I could automate. And there was also a job going at the University of Sydney, which was a pretty important part of it. Very enthusiastic people, good support, and surprisingly, in my view, very good funding in Australia. Much better funding for this sort of research probably than anywhere else in the world. And because the university were pretty naive and didn't know what I was doing, there was plenty of freedom as well to get on and do this kind of project. So, as fate would have it, at that time, Chris Corrigan had just bought Australian stevedores. And one of the alumni from our school, John Young, got in contact with me and said, well, what can you do in the container world? And in fact, we started out working on what they thought was the real bottleneck, which is the speed of cranes over ships. And we worked on new reeving systems, new control systems, and so on, which would actually speed up this process. And after we'd done this and built this large model, Chris Corrigan came to the lab and saw it and thought it was good and said, well, what else can you do? And I showed him a video of that freight vehicle, and he said to me, well, can you automate a straddle carrier? And I said, no problem. And so as it started at that point, we decided to go ahead. He was interested in investing to improve waterfront efficiency. They just bought these straddle carriers here. I have to say, these are pictures from when I first visited Patrick's 15 years ago. Bone age, archaic, would be an understatement for the way that Patrick's was at that point. So he bought us a straddle carrier. Here it is. They're quite big machines, 60 tons. And one of the great things about this is getting a second bite of the cherry. You've done it once. You've made all the mistakes. We had PhD students work on integrity and vehicle modeling and things like that. And we kind of knew some of the answers now. And to have someone come back and say, do it again, is one of those things that just never really happens except in a fantasy. So we got all the new research results we had, detailed vehicle model, high integrity navigation system architectures, provable levels of fault detection, all these things. We got the new straddle carrier, we had a great team, and more than that, because the CEO was involved, it was a long-term support. There was a recognition that this was not going to happen in 1 year. It was going to be more like 5 years or 10 years. And that's so important in these projects where really you are breaking this ground. And particularly also a flexible plan for how we were going to deploy it. It wasn't some idea that we were going to produce an X and then one day they were just going to put them all into the yard. There was a real thought process going on about how that actually happened. And at the time, if you remember, this is about 1997 now, we were having fun on the waterfront with the unions. Fairly well-known Minister of State these days, Greg Combet, said that what we were proposing to do was a fantasy, which is interesting in context of some of the things that he says now about robotics. But it was difficult. We had to work in a secret site somewhere in St Mary's, which is basically in Western Sydney and so on. And then gradually we started assembling the process. Again, the radar was very important to this because it was very important for doing all the navigation functions outdoors, collision detection and so on, integrated them into a complete system. And then around 2000, we gave our first demonstration of the system to the board at Patrick's. So this is, if you like, the first stage in a project like this. So we went on from there, and Chris Corrigan bought a new terminal for a couple $100 million in Brisbane, which he dedicated to automation. A number of people from the university team moved across to a new company. We looked at basically not just the whole process of how you automate a straddle carrier, the systems engineering and so on, but what happens with how you actually design an automated terminal. That is, actually worry about the safety, the interlocks, all the other processes that go on in that part. And that was a very important part of the partnership, where the industry person, actually who knew something about that domain, really helped you work that automation technology into the system that they were operating. And then in 2003, we ended up with a system with 5 straddle carriers on one terminal, Terminal 7 at Fisherman's Island, actually earning money off floating ships, shuffling containers, and this type of process. So it was a real major step. So a little later on, they took, again, a lot of people out of the university to help support this thing. They even hired professors occasionally to help them operate these things. Much higher pay working on the terminal than in academia. And finally, by 2005, we had 18 automated straddle carriers, and you'll see these are quite different. So they have no cabs, the drive systems are different, everything else. All the systems, the concepts are all integrated into here. And again, perhaps I'll emphasize a few things. You can never have a situation in which one of these things goes wrong, collides with something or whatever, because that would be the last time you'd be allowed to use automation. So it was very important here to get all those basic concepts operational. And it's grown now to 3 terminals up at the Port of Brisbane with about 35 straddle carriers. What's again interesting about this terminal, though there are operations people here, all the engineering that's associated with the automated straddle carriers, the operations and so on, is actually all run from Sydney. So it's all run remotely. Okay? So this is still, at this point, probably one of the most advanced commercially operational autonomous systems in operation anywhere in the world. And I also want you to reflect back a little bit on what perhaps the Patrick's terminals were like 15 years ago before we started this process. So there were a lot of important lessons in this project shared between both the company and the university involved. So I just want to say a little bit about the commercialization strategy, because I think this was an important lesson as well. In the earlier system that I showed you, the academics kind of owned everything, and it never worked. In this particular case, Patrick's basically owned the majority of what's going on. The academics and the remaining inventors own a little bit of what's going on, and the people who build the straddle carriers also own a sizable bit. And one of the lessons I learned from this process was that it's much better to own a little bit of something big than it is to own a large part of nothing. And I think that's a lesson that all academics need to learn, and indeed all universities, in fact. The commercialization strategy itself held a lot of lessons. So when we looked at what was going on here, there's probably about $150,000 worth of automation on each of the strads. But if you look at that, there's probably about 150 straddle carriers in Australia, so there's not much of a business, in some sense, building automation systems for these things. There's a lot more of a business selling automated straddle carriers, because they're $1.2 million each, right? So you can envisage, in fact, in principle, making a business out of this. But even better than that is actually not selling automated strads, but selling automated terminals. And this really helped us into a real recognition with what was going on with these things. Yes, there are savings with labor and things like that, but the real value in having an automated terminal or an automated straddle carrier is not that the straddle carrier itself is automated, but the fact that you vertically integrate it into the business. You change the business model. And that's the real benefit. So for the first time, these are savings here, but what the real savings come from is knowing where the straddle carriers will be all the time. Not just now, but 2 hours, 1 day in advance, and being able to plan and actually do something, change the way that you run your business. And that really was the main outcome for Patrick's. And I think it's a salutary lesson that in a lot of the applications we work in, it's the end users that actually benefit more than the people who actually produce the automation. So we've looked quite a bit at this, and I'll just point you down at the bottom here. Certainly there's a move now to move beyond integrated automation systems to provide perhaps automated terminals, and in principle, further into the future, perhaps even paper box type of operations. So there's another interesting outcome out of this. We had a startup company, Navtech, that came out of this, that developed the radars for the straddle carriers. They were a couple of my graduate students originally, and also, in fact, developed radars for other applications. And they've become an interestingly very, very successful company in a niche area, developing millimeter wave radar technology, 77, 94 gig technology, for things like debris detection on runways, counting traffic on motorways, security operations, and so on. And in fact, this year they won the Queen's Award for Enterprise. So this is another of these startups, which you'll see quite a few that have come out of the lab, that have made successes in interesting niche applications of automation. So one of the reasons I originally came to Australia was actually to work in mining. And there's a nice picture here. I love the Pilbara. It's kind of red and green, and it's got big holes in. It's a lovely place to work. It really is a grand challenge for robotics. It brings together all these different elements: perception, integrity, systems, and so on. And it's driven also, in principle, by a good model. There's safety, there's predictability, there's efficiency. There's all these things we saw in the container terminal in droves when you come to mining. And so when I first came to Australia, this is really what I wanted to work. And a lot of our early work, and there's a few people in the audience here, in fact, who'll remember some of our early work, we looked at basically that initial model we had. That is, let's automate an X. All right, so maybe we'll work on automated trucks. This is an example of using that radar for collision detection on a truck. Down here, there's a project that we were involved in, automating LHDs. But there was a real problem here, because the problem wasn't we need a robot. The problem was we need a better way of doing business. And I think at the time we didn't really understand that. So there was very much a lack of automation culture. I worked indeed with people like Andy Stokes, who are in the audience here, on key studies as to how you would actually catch the prize of automation. What does it actually do for the business? And so all of these sorts of things that we worked on at the time turned out really not to be successful at all, basic failures. And so we kind of refocused on looking, in fact, initially at least, at component technologies. And we worked with people like CRC Mining, another company that we started up out of the group, Accumine, which basically develops sensors which are some route towards automation. So, for example, this is the haul check system that Accumine produced, which basically gives you trucks guidance information. The trucks have still got people in them, but when the driver falls asleep, basically you know when he's going off the road, and it can warn him and everything else. Or radars, for example, that can image underground stopes or image from rope shovels. This is another system that Accumine produced, which is essentially a collision monitoring, collision warning system for large trucks and for haulier vehicles and various other things like that. So we had a large process of basically developing components for automation, because people just in some sense weren't ready for it or really couldn't understand, and indeed in many senses we couldn't explain what the benefit of automation was for mining at this point. And then things changed. At the height of the commodities boom, 2007, and I'd worked off and on with Rio Tinto over the whole process, there was a real thought that says what we really need to do is to talk about automated mining. Not automated trucks or automated drills or any automated X, but the whole process. How do you automate surface mining? And in many senses, the key to this problem is not so much let's build a robot, but it's worried about how you actually integrate everything together, how you worry about all the information that's in here and how you stick it all together, and only finally, let's take the person out of the cab. It's a lot more of a process-driven thing, very much in the lines of what I was showing you in the container terminal application. So the objectives in this case, and the program now has been running for getting on for 3 years, is really to take exactly those lessons, to improve safety, precision and efficiency, and in particular to vertically integrate the outcomes of that automation into the business. So the value is not in automating a particular component, it's propagating the benefit of that through the entire business, that precision, that efficiency, the information you now have, and so on. And in many senses, the same results apply. Who benefits from this? Ultimately, it's the end user, because that's what is becoming more efficient through that process. It's that systems integration with the user, it's the domain expertise, it's the information and so on. Of course, equipment manufacturers still have a significant role in this. You need to have automated equipment, drills, trucks, or whatever it is that needs to go into the mine, but you need to be able to integrate those things together to get that benefit. So the Rio Tinto Centre for Mining Automation has been a very interesting partnership. It's probably one of the largest investments by a company in a university group ever in Australia. And it basically is a good group because it has one mission: automate surface mining. All right? And if you like, it's not just about automating a particular component, it's about how all those things to work together. So the focus is very much on information systems, on how the whole thing gets integrated together, the research that's actually required to do that, the development process that pushes it through, and so on. So the university team has now grown to about 50 people, including graduate students. And the other real thing, a lesson that we've learned, is it's not a one-year project. It's a 5-year or 10-year project, potentially even longer, to make sure that this whole process is followed through. And again, importantly, it's supported from the very top level, which is what really drives this thing along, a long-term investment for this. Equally, on the other side of the university team is a team from Rio, who take the stuff okay, who really focus on how you're going to get the best use out of it, how we're going to implement it, how we're going to support it in the field. Now, a number of this team, in fact, they've all moved down to Melbourne this week, come from the university. So if you like, there's a process of handoff where we've got the research people, we've got the engineers at the university, and then as things mature, those people then take it both to Rio and to operate it in the field. So there's this whole virtuous process that's going on in here. So as I said, architecture, information and control are really what's going on in the main part of the center. So we worry a lot about how we're going to build a design and architecture which will support not just all the information systems that Rio use and all the new data fusion concepts, and I'll talk a little bit about those in a minute, but also, for example, how we plug in information from drill rigs, from different types of sensors and so on, and how we use the same architectural structure to plug into things that might be provided by another OEM, whether they be trucks or drills or explosives carriers or anything like that. And it's really a process of understanding how all that information, all those control attributes all come together. So there's been a lot of interesting work that's been going on here, and I'll just touch very briefly perhaps on one area. A big issue has been to actually use all the information that's generated in the mining process. So there's a lot of work that goes on, for example, using different types of sensors to build up real-time pictures for what's going on in the mine. Not just on the surface, but also under the surface, using, for example, drilling information that's obtained when you drill blast holes to come up with, in real time, estimates of what's going on in terms of the mineralogy, the surface structure, contaminants, things like that, so that you know what you're doing in terms of planning, efficiency, operations, this whole sort of thing. And again, I'll emphasize at this point, it wasn't a question of getting the man out of the loop. All right? It's really a question of how all these things come together to create a better product at the end of the day. And also at the surface of the thing, in this case integrating hyperspectral information with laser information and visual information to give you some real-time determination as where the good ore is, where the less good ore is, and so on and so forth, so that perhaps you can use that to control what's going on at the face in terms of loading and so forth. So capturing the prize, let's come back to the original thing. I think what's been interesting about the Rio Centre is to really understand that it's the end user. I think this is very important in an Australian context as well, because we have so many end users, okay, is that the technology that the end user controls, ultimately they're the people that benefit from it. So in this case, Rio controls all these enabling technologies, the information technologies, the data fusion technologies, and so on, and has a strong process of integrating that vertically into the whole way the business is run, the whole way that you actually do mining. And also, in addition to that, then using that leverage to try and encourage additional OEM engagement. And from that, developing the commercial outcomes. This remote operations centre that's been a little bit about it in the press. So this is a place at Perth Airport where now a lot of the mines in the Pilbara, a lot of their components in the mine are all operated remotely, the autonomous drills, the architecture for the integrated mine, and so on. It's a really exciting time, I've got to be honest here. There's a real transformation in mining coming, perhaps one that doesn't happen more than once in every 50 years. And it'll make not just a difference to what's going on in these particular mines, but it will make a major difference to the way that the economy works in Australia. So let me kind of go back to the beginning. You're beginning to see this story of a lot of different threads that are all coming back to the same sort of thing. And I'll go back to this robot here. You'll notice it looks very boxy. Okay? And that's because it was kind of designed to be modular. We built a lot of these different modules with sensors in, with controllers in, with different types of functions, and then we developed algorithms that allowed us then to build robots out of modular components. And every one of these boxes has got a computer in it, and there is no central computer in here. It's all basically just networked together. They exchange information using some fairly clever algorithms, and they use that to basically fuse information to decide how they're going to do control and so on. So this was a very interesting idea at the time. We developed a lot of ideas in network data fusion, network control, all these types of problems. And we talked a lot about things like network sensing and so on, and nobody was interested. You've got to remember this was back in 1990, all right? So I then dropped the whole idea. I came to Australia, and then by about 1995, 97, that sort of thing, people were saying, oh, network sensors, network-centric warfare, all these kinds of things. And it turned out a lot of the original algorithms that we developed for this kind of project, this one here, turned out to be extremely valuable. So I got back together again with a company that I'd worked a great deal with, BAE Systems, in the past, and they're basically, this is an interesting commercialization lesson, because unlike Patrick's or unlike Rio, they are not the end users of the technology. They're basically technology developers themselves, and they take that technology and sell it on to defense forces in the form of various products. And what they wanted in this case was a defense demonstration of all these network data fusion principles, network data fusion theories, and so on, both in the sense of how information's put together and how you get multiple things to cooperate and coordinate and so on. So in this case, it's very interesting because our role is no longer the direct commercialization route. Our role in this case is to demonstrate technology and get it inserted into a company as part of some global supply chain. It's a very different model from the sorts of things that we saw before. But again, this was a tremendously exciting project, and I often say at this point, if we had known how hard these projects were going to be, we would probably never have started. So this basically shows a demonstration of many UAVs all flying together. There's nothing on the ground in this case, no controllers on the ground. Okay. What happens is these aircraft are actually downloaded a potential target map of what's going on the ground. They then basically start talking to each other, and then on the basis of what they say to each other, and for the academically inclined here, they talk in terms of posterior probability distributions. Okay. They then decide which targets they're going to visit, which ones, how they're going to search, and so on. So all of these things, while they're in the air, you've got no idea what they're going to do. All right? So this is a really scary project. Make sure, I often say to my students, you've got to make sure the code works first time. All right? And indeed, we have lost more aircraft here. And the other thing that we developed in this process was to try and apply some pretty advanced machine learning algorithms as well, where you basically do things like fly over with a camera or drive past with a camera, and you want to be able to, for example, identify trees but not bushes. That's a pretty hard algorithm, okay? So what is it that makes a tree and a bush, and so on? What makes a tree look like this on the ground and look like this on the air, from the air? And how do you fuse that information together? But again, crucial technology for a lot of the sort of operations that people like BAE, and indeed now also in areas like mining, and we'll see a few other applications in a minute, want to actually apply this to. So it's had some really impressive outcomes, in fact. The Type 45 air defense system is now based on a DDF technology. The future UCAV, you'll notice that this is actually being demonstrated in Australia. You can see the red ground behind it, are all based, again, on the DDF type of technology, and also now in ground sensor networks, a whole variety of different applications. I think the important thing here is that maybe we don't commercialize it as a startup company or as some of the other things I've shown you, but it's been very important for us in Australia to be part of this global supply chain in which this technology gets integrated and so on and so forth. Some of the other spin-offs, which I think are interesting, is we've gone into using UAVs for agriculture, and this is spun out of basically exactly the defense things, uses the same algorithms, but instead of finding targets on the ground now, we find invasive weeds. Okay? Same types of machine learning algorithm, but now we can find things like prickly arcadias, we can find sylvania, lots of other very specific types of weeds in different environments. In dam areas, you can see this area here is a clogged up dam, and you'll see the spray booms on the side of the helicopter here. So it can go along, find the weeds one by one, and spray them one by one. Okay? So no more spraying over the whole area. This is, again, exactly a great application for this type of robotics technology in Australia.